Welcome back, lesson 4 for Year 11 Physics Double Science. Make sure you're on page 30 and just put the title lesson 4 and date at the top, please. Quick recap on what you've learned previously, which are the Newton's laws of motion 1 and 2. What forces are, weight, and how they affect the motion of objects. Today we're specifically looking at objects falling through the air. It's part, or I should say section F on the specification, and it reads forces. To learn how forces and their effects explain the behavior of objects moving through the air, including the concept of terminal speed. So this could apply to vertical or horizontal motion, and we're going to look at some examples with explanations today of a skydiver reaching the maximum speed. We need to be able to explain how terminal speed is attained, and the term terminal speed will be used rather than terminal velocity. Remember, speed and velocity are very similar. Seen in the specification, they're going to use the term terminal speed. The only difference between speed and velocity, remember, is velocity has direction as well as a size. It's a vector, whereas speed is a scalar. Sometimes we use the word magnitude, remember, instead of size. Okay, back to today. Well, before we start this, I just want to go through a quick animation that explains this whole concept. This is a piece of software, again, you can access via GCSE website. It's useful to help you understand what terminal velocity is. So first of all, ask yourself, what are the forces acting on the physics man here? Well, of course, you've got his weight acting down, but that's been balanced by the tension in the rope acting up. So his velocity at this point is 0 meters per second. Remember Newton's first law of motion? When the forces are balanced, either the object stays still or moves at constant velocity. Now, the animation here is paused. So this man isn't levitating, he's not defying gravity. It's just paused so we're able to analyze what's happening at this point. Now the forces acting now, the tension here, the snap you can see here, has gone. So the only force acting is the weight acting down. The resultant force now is no longer 0, it's acting downwards, it's the size of the weight. So he's going to accelerate. As it says here, at the instant the rope snaps, the only force acting is weight. By Newton's second law, weight will cause him to accelerate downwards. So as his velocity increases, so does the air resistance opposing his motion, and you can see that by this blue arrow getting larger. Eventually he will reach a speed where the air resistance, the blue arrow, equals his weight, the red arrow. At this point there is no longer any resultant force, they cancel each other out, of course. The forces are balanced. Now this is called his terminal velocity. For humans, it's about 50 meters per second, and if you hit the ground at this speed, as it says, you're in trouble and you'll probably die hitting the ground at that speed. So that's why, of course, you need a parachute. So let's open the parachute. Again, we've paused the animation. What happens to the air resistance? And are the forces on the man balanced? What will happen next? 3 questions. Well, let's look at the explanations. Of course, the air resistance is going to increase because there's a larger surface area for the air particles to hit. So the air resistance up is larger than the weight acting down. Now there's a large resultant force acting up. Now please don't think that the physics man here is going to accelerate upwards. That's a common misconception. He's going to decelerate. Sometimes when you see real life footage of a parachutist opening up the parachute, it may look as though he's moving upwards, but it's relative to the other skydiver that's filming the skydiver, the skydiver who's opened the parachute. So he's going to decelerate. And because he's decelerating, the air resistance here gets less because the speed decreases and therefore the air particles hitting the parachute become less. And by the way, you can always pause the video and read the full explanation here. So he's reaching now a terminal velocity of about 5 meters per second. That's 10 times less and can land safely. Let's apply that concept to this question. Bertie's dropped his phone. What do you need to do? Well, you need to answer questions 1 to 6. 1 to 6 are on the next page. So, which force surrounding the mobile phone remained constant through its journey? Before we look at these questions then, let's look to see what's happening here. We've got 3 different positions of the phone's journey. 1, 2 and 3. The weight force remains constant, and we'll label the weight force as 2.4 newtons. The phone doesn't gain weight, it doesn't lose weight just because it's fallen through the air. However, the upward force changes, and the upward force of air resistance changes with speed. The larger the speed, the larger the air resistance. And the word we use, of course, is proportional. As the speed goes up, the air resistance goes up or increases. Therefore, the lower speed will be at the start of the journey. Therefore, this is 0.3 newtons, 1.7 newtons, and therefore 2.4 newtons. If we were now to work out the resultant force, number 1 is 2.4 take away 0.3. It's going to be a downward force of 2.4 take away 0.3 equals 2.1 newtons acting downwards. Resultant force acting downwards, and you all know by now, using Newton's second law of motion, the object will accelerate downwards. So question 1, which force surrounding the mobile phone remained constant through its journey? That's going to be its weight. So you answer here. Calculate the resultant forces for all 3 stages. Now I've done question or position 1, I should say, above, with the resultant force of 2.1 newtons, and I've drawn that in the box there. You need to do the same now for 2 and 3, position 2 and position 3. I've highlighted those 2 boxes for you. What stage is the phone accelerating at the fastest? And explain. Don't just put down a number. Explain why it's accelerating at its fastest. And the hint here is acceleration is directly proportional to force. So the bigger the resultant force, the bigger the acceleration. Question 4. At what stage was the phone not accelerating? And explain in terms of resultant forces. You can do that just using the same hint. If there's zero force, there's zero acceleration. And which stage was a constant top speed reached? And what is the scientific term we use? Well, that's terminal velocity. Question 6. The bits of the phone after it was smashed still had a weight. This force is now balanced by... Now I've answered this one for you because that was a tricky one. So the bits of the phone on the floor were balanced by the reaction force of the ground acting back up. That's page 32 complete. So just pause the video and complete that page, please. The activity on page 33 is helping to develop your graphing skills and improve your knowledge of terminal velocity. What you need to do is turn the words into a graph. You'd have heard the age-old adage, a picture is worth 1,000 words. Well, it's often the case with graphs as well. If we look at the first point here, where it says when I say here, the part that's highlighted in blue, between 0 to 6 seconds, and he jumps out of the aeroplane and increases the speed from 0 to 54 meters per second. You plot that on the graph underneath. The scale has kindly been added in by Mr. Ruddy for you. You need to label the axes, of course, and I've just made a start by drawing in the first part of the journey up to 6 seconds. And in fact, I've in the second part, which is where terminal velocity is hit, so 6 to 23 seconds, her speed stays the same, which would be 54 meters per second. You then complete for parts 3, 4 and 5 for Annie's parachute jump. Next page. What you need, this is a matching activity for you, where you need to match the letters A, B, C, D and E to the pictures underneath. I've done B for you. If you look at B, you can see that the size of the arrow acting down and the size of the arrow acting up are the same. And the only other picture where that's the case is here. But because the parachute is up in that box, the terminal velocity is going to be a lot smaller. In fact, it's going to be D. But I don't want to give you all the answers. So you've got to match up the letter and write them in the boxes there. Really gets you thinking, this one. If you're unsure, just go back towards the start of the video and look at that animation again. And then you've got to turn the graph from pictures into words. So as the velocity increases, the air resistance will increase. Forces are now balanced, which leads to reaching a constant velocity called terminal velocity. So that then matches part B. The remaining page, page 35, is asking you to write down a title, a risk assessment, results and conclusion for an experiment, excuse me, or an investigation. And this investigation is one of the investigations or practicals that you need to know for the course and the exam. I'm not going to read through the whole method, of course. However, I've videoed, with the help of Mr. Hancock, this particular practical that you would in normal times be doing in lessons, which we'll watch in a moment. And then what you need to do is use this results table underneath here to make your conclusion. And when you make your conclusion, always go back to the independent and dependent variable. And the independent and dependent variable can be found on the table. And what we're doing is changing the number of cake cases and seeing how that affects the time taken for the paper cake cases to fall. It sounds a bit abstract at the moment because you haven't watched the video. Watch the video, use this data to help you write your conclusion. Your conclusion will be something like this. As the number of cake cases increases, the terminal speed also increases, and we can see that from the table. The best conclusions, of course, have a scientific reason behind it. So the scientific reason or explanation will need to include how the air resistance and the weight, the two forces acting on the cake cases, change. So what you will say is that the more cake cases that are added, the larger the weight. However, because the surface area remains the same, the air resistance acting up on the cake case needs to be larger to balance out the weight force acting down. Therefore, the larger the number of cake cases, the larger the weight and the higher the terminal speed. That brings us to the end of lesson 4. But before we finish, of course, watch this video that will support you completing this page. And of course, as always, please complete the plenary assessment, but also, importantly, complete the written assessment that goes with this lesson so that your teacher can give you some feedback on, yes, your knowledge, but also your literacy skills. See you next time. Bye. Hello, this is the experiment to calculate the terminal velocity. In this case, we calculate the terminal velocity of one of these, a cupcake holder. And to do that, we need to know two things: the distance travelled and the time taken. We're going to be dropping the cupcake holder from this point here on using the clamp stand as a pointer, and it's going to fall a distance of 1.5 meters to the floor. So 1.5 is the distance. The time taken, we're just going to measure that with standard stopwatch, and we'll divide the distance by time. Now, in order to get reliable results, for each cupcake that we drop, we'll do it 5 times, 1 for 1 cupcake. So you drop it 5 times for 1 cupcake, 5 times for 2 cupcakes, and the same for 3 cupcakes, and so on. If you watch when I drop 2 cupcakes, and I'll record the timing of that in a moment, you'll notice as we increase the number of cupcakes, 1, 2, 3 in this case, the cupcakes form more quickly. For the latter part of the video, I will share with you the results that can go into your booklet. You can calculate the terminal velocity, but what you'll notice is that the cupcakes are falling more quickly when we have a larger mass. Each cupcake is 0.3 grams. So you need to think about what are the forces acting on the cupcake. You've got the weight acting down and the air resistance acting up. And the resultant force is weight take away air resistance.